All right, morning class. Thank you guys for being here today. We're going to work today on moving between velocity and acceleration using the power rule that we learned yesterday, moving between position and velocity. It's basically an application of that same kind of thing. We're just adding in a third element. So when you start with position, you take the derivative. As you know from yesterday, you get velocity. If you do that one more time, you get acceleration. So we're going to start by reviewing what we did yesterday. Right here we have the graph s of t equals t squared. It's our position graph. What would the derivative be here? If I'm taking the derivative of t squared, what am I going to get? 2t, exactly, good job. So we know that the v of t here is going to equal 2t. And so then up on the board, that's going to look like this. All right, so moving on a little bit, right here we have a velocity graph. Our velocity is explained by 3t squared plus 2t. So can someone come up and show me how to derive that to get the acceleration, or v prime of t? Someone? Sam, yeah? Sure. Great. You can go ahead and explain what you're doing while you're doing it. Sure. Actually, I'm going to have you use a different color because I already used blue, my bad. There you go.
So we'll take this number down and multiply it onto the 3, and we'll subtract 1. And there's a 1 here, and we'll take it down and multiply it over the 2.
Great.
So we have 6t plus 2.
Great. Now go ahead and draw that up there. Does everyone understand what he did there, or why he got 2 on that last one? Yeah, Noel.
So I have a clarifying question.
Yeah.
So you took the 1 and multiplied it by the 2, then what happened to t?
Oh, great. So basically what happened there is when you take the derivative of 2t, thank you, Sam. You take the derivative of 2t, there's actually a 1 attached to this t, it's t to the first, but that's implied, we don't usually write something to the first. So when you're taking the derivative of that, you follow the power rule just like we always do. Bring that 1 down, multiply it by 2 to get 2, and then when you subtract 1 from 1, you get 0. So you get 2 times t to the 0. And as we know, anything raised to the 0th power is going to be 1. So that gives us just 2. And thank you, Sam, for drawing that up there. So now we're going to work backwards a little bit. So right here, our acceleration is 3. Can someone come up and show me what that's going to look like on the graph? Oh, yes, Jack. I'm going to have you use red for this one. So acceleration of 3, what's that look like?
I think that's a constant.
Great, good job. You did your reading. Well done. So right, this is going to be a constant. It's a straight line. So in the real world, what's that going to look like? It means that your acceleration is increasing constantly at 3. So does anyone know what unit acceleration is going to use? Yeah, what's up?
Meters per second squared.
Meters per second squared, exactly. Can you explain how you got there?
So we know that our speed is just meters per second. So acceleration is just how much faster you're going per second. So you're going meters per second. It's just acceleration over time.
That's perfect. So yeah, when we derive from meters or from position, we have meters, and we derive to get meters per second. Meters how position is changing over time. Then when we get velocity changing over time, that gives us our acceleration. It's kind of a cool thing about physics is if you take that first derivative to get from position to velocity, you take it again to get from velocity to acceleration. If you take it a third time, you get how quickly the acceleration is changing, and that's called the jerk, which is cool because you can imagine being in a roller coaster or something and it gives you that little jerk. That's how quick your acceleration is changing. Interesting little piece. Also later down in the list there's snap and crackle and pop. Physics is fun. So what we're going to do now is we figured out that our acceleration is 3 meters per second, and we know what that looks like. So now I'm going to show you how we would get to velocity and position from there. All right, so as we did yesterday, oh yes, Noel.
Is our acceleration still meters per second squared?
Oh yes, it is. Thank you.
Okay,
Good catch. Acceleration is meters per second squared. So in order to get from acceleration to velocity, just like yesterday when we got from velocity to position, we're going to do an integral. So we're going to integrate the acceleration with respect to time. And so that's going to be the integral of 3 with respect to time. And then, when we actually integrate this, does anyone know what we're gonna get? Yes, Jack.
I think we'll get 3t plus an undetermined constant.
Exactly. Good job remembering that. You really did your reading. This constant is important because that tells us where the graph is going to start. From the 3t, we can determine the shape of it. We know it's going to be a straight line, but we don't know if it's going to intercept the y-axis at any of these points. So let's move on and do the position one, and I'll show you how we can figure that out. So let's say we know that, I'm going to do a little erasing here. We know that our velocity equals 3t plus an undetermined constant. Taking the velocities integral to get position, we would take the integral of 3t plus c, and that's going to equal our position, which, can anyone guess what that's going to be? The reverse of the power rule that we did yesterday.
3 halves t squared plus ct plus a different undetermined constant?
Great, well done. So yes, absolutely. Because we're transferring over this constant right here, that's c to the first, so we need to, when we're integrating back in for time, we need to account for that in there. So our position is 3 halves t squared plus ct plus, and we're going to call this other constant d, just so that we're not using the same variable too frequently. So let's say that we know when t equals 0, at the very start of this experiment, when t equals 0, we know that velocity of t equals 5, and we know that the position equaled 10. How would we go about solving that one? That's just simple algebra, right? So we plug in our velocity in here, 3 halves t equals 0, 0, plus c times 0, plus d, when we know that equals 10, just using position right now. 10 equals d, we can figure that one out. And then plugging in for the velocity, we can figure out that 5 equals 3t plus c. T equals 0, so 5 equals c, easy enough. So then our final calculation for position is going to be that position over time is going to equal 3 halves t squared plus 5t plus 10, using our c and d constants that we found just now. So does anyone have any questions before we start moving into some independent work? Okay, great. I'm going to pass out a worksheet. One of the questions on here you can see discusses inflection points. Don't worry about that one for tonight's homework, because that's going to be in tonight's homework. You have to do the readings to get to that. We'll start class tomorrow by going over inflection points and that, and any questions you have with the worksheet. You guys have a good day. Thank you.